And homework 2.3, number 8, was computing average velocity with time interval h being 0.1, right? And at how many points were there? Like 5, 6 points, or several points at several time, several instants. How about that? Does that make sense? Yeah. At time 3, time 3.5, and things like that. So how was that experience? There were only like 5 or 6, so you could have done that just manually, So let me show you. If you do that manually, I think it looks something like this. All right, is it showing? So I calculated 3 to 5. That was the problem. 3 to 5 increasing by 0.5, right? And it's weird that the sage command does not include the last value you specified, so I have to throw in manually. I'm going to throw in 5 to that list. So that is 3 and 3.5 and 4 and 4.5. It's just the purpose of listing it. I'm not really using t in the next step. So h is fixed. H is going to be always a 0.1. Instead of typing in 0.1 all the time, you can use this h. You type in h equals 0.1, and you can use h later on, right? In the sage. So instance time a here is a 0.3. That's the first one that you try. So you compute this formula. That's exactly the formula for the average velocity, right? Between a and a plus h. So this is the beginning time, and that's the terminal time a plus h. This is the displacement, and this is h is a time interval. If you calculate the first average at 3 with a time interval of 0.1 second is a 7.5. Does it agree with the first number you didn't remember what those numbers are, as long as you print it out and it looks okay, and then you probably didn't pay attention to what those numbers are. So I manually did that, like 3.5. You repeat it, copy and paste, just changing that number, right? That's the only thing that changes. You repeat it several times. So I also show that how to do that in a one for loop. If it is like 100 points and you don't want to do that, repeat it over and over. So there's something called for loop, and you can put it in there, let the machine do that automatically, and then this code will repeat 100 and whatever the number of times you want. But that's all it takes to number of coding. It's all it takes, and then it'll generate lots and lots of data in here. All right? So you will have that. So knowing that, it's not that hard, so I hope you'll be able to learn this one eventually. So those are the velocities. And I also ask you to go back to section 2.1 or exercise 2.1 and ask you to compute some average velocity from that section, right? Those were okay? You have a clear idea about average velocity? All right. So let's review briefly about this physics problem. Motion of a particle. What kind of motion is that? It's not a two-dimensional or three-dimensional motion. It's up and down or linear motion, right? Is in that path, and from that we consider average velocity. That's what we talked about. So if you look at actual motion, here's the vertical axis, y, and what is the good letter for the horizontal axis in this motion situation? T, representing the time, right? The actual particle is actually on the y-axis. It never leaves the y-axis over there, right? That's how we look at the motion. But let's say that was an example. That was the initial position, and let's say, position after expanded over time, it looks like this. But its actual motion is over here, and that's the graph of y equals st. Make sense? All right. So we have an idea about average velocity. But if you look at this one as a graph of just a function, y equals st, and what is the equivalent? Average velocity is a number as a geometric object. What is the equivalent notion of the average velocity? What was that? Something of some line, right? Yeah, slope of what kind of line? Yeah, secant line. So that was the idea. If you choose 2 points, A and B in here, and you go up, you find this 2 position, and you connect that. Let me use a different color. If you connect that 2 points with a straight line, and there's a unique line that passes through two distinct points, and that's called the secant line. And slope with the secant line is what we're talking about, and if you think about it, that's exactly the average velocity. If you interpret that graph as a position after t seconds or time t, right? So those two things are the same. Let's go ahead and look at this example. We're going to stick to this example today for quite some time. ST being it's slightly different from last time, it was slightly simpler. I realize that's better to show them the picture in the correct scale. So let's say this the position after t second is discovered to be obeying this formula, sine 2t minus a cosine 2t. All right. So I think I typed those in here. So I'm showing that st is given by sine 2t minus cosine 3t, and then I plotted that curve and between 0 and 6 seconds, and I stored it in something called position, and then I display the position just by typing a position, and that's the graph of the motion. Okay, so I think I'm going to copy this. All right. So why don't we go ahead and write down the average velocity formula. Once again, average velocity between t equals a and t equals b. If you have practice calculating this one, so I want you to go ahead and write down this formula. What is this letter I used, this average velocity? I used v subscript a, right? And this position is given by that st. So use st with not actually using this explicit formula. Use st and a and b and write down the average velocity formula, all right? So I changed the picture so that it's in the correct scale. We're going to calculate the slope of something, so it better be accurate. That's why I changed it. It's s of b, right? Minus s of a and divided by b minus a. That's the average velocity if I give you two time slot, right? So next thing is exactly the same thing, but in a different context. So we're going to fix that time interval h to be something, right? Fix that, the time interval. Fix time interval, just like that problem you did in 8 or 7, time interval a, and compute the average velocity with the time interval h, interval h, at instant times equals a, right? So it looks exactly like that, but it should be described in terms of a and h. Remember that? So why don't you go ahead and write that? It was actually stated in the bottom of the homework page that that thing is in terms of a and h. So go ahead and state that one. I hope it looks something like this, right? It's just b is replaced by a plus h, and denominator can be simplified. Time interval b minus a is just simply h, right? So these are the terminologies for motion, but if you look at the graph of a function, what was the notation I was using? There's a slope of secant line, right? So I use this m subscript s, and this is also m subscript s. If you look at this, it's purely just the something about the graph of a function, not a motion of anything, right? It's a geometry problem. Okay, so I'm going to go ahead and actually look at this as a new perspective. H is fixed, so here's an algorithm I'd like to give you. I think I said that at the end of yesterday's class. I'm about to describe an algorithm, right? That's how we started this course. I give you a number A, and you understand the procedure that is described by the algorithm, all right? So fix the function. Let's say this is a part of the, think about the way I describe the algorithm for an inverse function. St is the position function that's given up there, and fix, in this algorithm h never changes. A fix time interval h, that's number. Algorithm starts like this: given value a, and you understand what to do with that a, right? So what we're going to do is that compute the average velocity with interval h at time t, time a. That's our output. You do all that thing, compute and thing, and the output is that VA. Is that right? So this is a description of algorithm. It is not a formula. It's just it's a direction, and then you understand this direction is clear, right? Is that clear? You have a position function given, and time interval h is fixed, like 0.1 or 0.01. And if I give you a number a, and you compute the average of velocity at that instance a with a time interval h, and then you get that average velocity as a number, right? That number is your output VA. So input, you do lots of things, and your output, right? What is this whole thing called again? The fancy number, the name for this instruction is a function, right? Does it look like a function? Right. Function doesn't have to be given by a formula. It's a clear instruction, then it's a formula, right? Sometimes you can summarize it into a formula and sometimes not. Make sense? So rise of a new function. So I'm going to call that one average velocity function. This is non-standard term, but it helps us to see what's coming after that. So rise of a new functions. A new function. Derived from where? Position function st. If I give you a position function st is a function, right? Position after t seconds. I can create a new function, right? What is a new function? If I give you a, you do that, and your output is a average velocity. Make sense? So that gives you a new function. Call that function. We're going to give a name, right? When you have a function, you should give a name, f and g and h, like that, right? So I decided to use this notation v bar. This is also non-standard notation, but I'm trying to distinguish all the slightly different notions which the engineer and physicists tend to abuse. VA is a number here, right? But in physicists and engineer, we'll turn that into a function. VA is now a name of a function and things like that. They abuse a lot, and I'm trying to distinguish all the notions as much as possible. But eventually we'll abuse a little bit when you're just doing an application problem. But in mathematics, it has to be that way. So this V bar is not a number, right? It's a name of an algorithm. It's a name of a function. How do you turn that into a number? You plug in your input value, parentheses a, and it becomes number, right? So this is that, and the V bar of a is a number, right? But what that really is, the velocity. It's the velocity, average velocity, right? Does that make sense? This V bar encodes a lot. I give you a, you go through all that calculation and spits out a number. That number is the average velocity at that instance a with time interval h, right? Okay, does it look like a function? The V bar summarizes this description. Behind the formula, it's more complicated. All right, so here's maybe something that it follows quickly. Thus, V bar, name of a function, if you have an input a, can somebody write down the formula? Although this is the way it's defined, right? If it's defined, sometimes there is a formula and sometimes not, but do you think there is a nice formula for V bar a? What is it? V bar a represents what? It's a number, right? It's average velocity at where? At a, with a time interval h. That's a description in words, but is there a mathematical description? Closed formula. What is that? That thing right there, right? So that's a formula right there. It's S of a plus h minus S of a divided by h. That's the thus part. I'm not defining it, right? I defined it earlier up there using words, and everybody understood that's a very clear instruction. Because of that, we have a formula. V bar a is this formula there. Okay? So actually calculate lots of this function value, and its sin t is difficult to calculate. We have to use calculator. The Sage is the best way. So I'm showing you how to define this new function, right, in Sage. Go into Sage, 913. All right. So I have to kind of click in there. How do you do that? To maximize a little bit. Oh, there. Kind of retarded. There it is. All right. I'm going to insert it there. All right. ST is already defined, right? So let me pull it up. I'm going to define new function. Let me go ahead and change that A to also a variable so that it looks a lot like what we just did. So I declared A is a variable. It's a part of the variable. And the name of the function is a vbar, right? So I'm just going to use a vbar like this. Is that right? That's the name of the function. And you define an A to be whatever the formula we have. Okay, what was the formula? S of A plus H, right? That's the average velocity, minus SA, and the whole thing divided by H. I don't think I define H there, so I have to give H to be like a 0.01. It's 100th seconds, right? A lot shorter than what you guys calculated. So I define the function like that, right? Well, that's surprising. I didn't know it does all that. So let me go ahead and calculate some of the v-bars. So the v-bar at 1 second. What does that mean is that if you plug in A equals 1, we go through that formula, and let me change the 1 point. So it calculates the average velocity at 1 second, right? And between 1 and 1.01 second actually, right? Because H is the time interval, 100 seconds. Is that right? Okay, so I'm going to calculate that. It says negative 0.4716. Let me go back there and see if you agree that at 1 second is about here, right? About there. If you go up, it's almost the top position, but it says it's actually coming back down at that position in 1 second. Does that make sense? Let me go ahead and change. What's your expectation about 3 seconds there? What do you think the velocity? There's a positioner there, and 100 seconds later, is it going up or down if you're looking at this position 3 there? Right, 100 seconds later, it seems like position is slightly up. So we're expecting positive velocity or negative velocity. If it's going up, it's a positive velocity. So let's see what this one gives us. Is a v-bar over 3 seconds. It's supposed to be a positive number, and it says actually 3.12. Split seconds later, you're like moving in 3 units per second. That's the information in average velocity. Does that make sense? Right, so you can build into like that, and we can quickly calculate all the average velocity in every position by just simply calculating like this, right? So with the Sage help, and then do we feel like we clearly defined the function in our mind and also defined in this machine in Sage, right? So this new function is defined, derived from the position function, right? So this is a stage we call function is defined. The first thing is that you try to evaluate that function at each values. That helps you to understand what the function is, right? So this one is called evaluation. We evaluated this function. Why do we do that? Just to understand the definition a little bit more, right? So what was a v-bar of 1? Turns out that was negative 0.747. It was negative 0.47, right? And average velocity at 3 seconds is roughly 3.12. That tells you how fast it's moving over 100th time period at that instance, right? Knowing that this motion is not too crazy, over 100 seconds, that's pretty much the velocity that doesn't change. If you go to next time period like 3.1 second, you don't expect this changes all of a sudden to -3 or something like that. It's pretty much the steady speed for a short period of time. Of course, if you look at it 1 second later, average speed changes, but over a short period of time, the average speed doesn't change quickly, right? So this is good information by looking at a 0.1. So that's evaluation stage. In the pre-calculus level, when the function is introduced, first thing you do is evaluate. And next thing you do is you sketch the graph of this function. what is the deal about the graph of a function? Graph of a function tells you the behavior of the function value overall. The global picture is not like what is the value at 1, what is the value at 3. So the graph is ultimate representation of the behavior of the output value as input value changes, right? It sounds like the limit thing that we've been doing. The graph is ultimate global presentation of the behavior of the function value. That's why we're sketching the graph of this. So this VT is a function. When you sketch the graph of the function, here's how it looks like. This is often confusing sage. This is a y-axis and horizontal axis again. What is that? T. And we're sketching the graph of what function? Newly derived function, right? Not ST. What is that? V bar T. How about that? Switching A from T. Isn't that just A is a dummy variable? Whatever you plug it in is called A, right? Can we switch to T? Any time position T. So we understood the word description of V bar T, and we came up with a formula, and we evaluate using the technology a couple of values there. So I want you to go ahead, and here's 1 and 2 and 3 and things like that. So at 1 second, what was the velocity? Anybody remember the velocity? Average velocity at 1 second? Negative 0.47, right? So I'm going to go ahead and mark that negative 0.47 down there. This is 1 unit down there. So I think roughly down there is negative 0.47. Is that right? So I give you a value. Although the average velocity is a little abstract notion, the motion is position is concrete. This is what you see, right? But the velocity is not what you see. Is that right? Velocity is our abstract notion. But what we just did is the notion, the abstract quantity, the notion and the quantity that is associated with abstract notion, we turn that into a position. All right? If you go to the hospital and there is just this pumping thing up and down that as you breathe in and out, whatever that the device is, that's kind of, presentation, visual presentation of an abstract thing that's going on inside our body. Just like that, we turn that into height. The velocity is not height, but we turn that magnitude into a height. That's what we did, right? The graph of a function. So here's a graph of some abstract, notion and quantity. We turn that into a visual height so that you can compare the magnitude to each other. Does that make sense? So what about 3? At 3, what was the velocity? 3.1, right? So it's way up there, something like that. So we select 1,000 points in between 3 and 0 and 3 seconds. We can plot all that velocities, right? But we have a formula. Why don't we just go ahead and plot that function, right? Whenever you have a formula, you can use Sage to plot that function, right? That's what I'm going to do. So here, going back, and after understanding the meaning of the graph of a function, and here is next stage, plug it in there. I'm going to kill that. Go back here. So that's going to be the velocity picture as a plot of what is that function we're plotting in Sage? What is it called? V bar of t between 0 and 6, right? So we looked at 2 points, but I'm going to change that color to what we've been doing before. And aspect ratio, I think it's controlled by show. All right, but no, I have to show in here as well. Aspect ratio 1. Doesn't have to be that. All we need is this number to represent it, so aspect ratio is not important. So it didn't show anything because I only stored in here, and we want to see the value. The function looks like this. All right, let's go back and interpret that 2 values that we calculated. So I'm going to go ahead and copy this. Go back here. All right, that guy goes to one side, and this guy go to the other side. So let me do that here. It's easier. Hope you can fit in. I think I can fit in like this. So I put these two things together. So this was a graph of y equals what? Position, right? ST. And what is the graph of this one? Is y equals v bar, the velocity after t seconds, right? So at 1 was over there, and position was whatever the unit. I've kind of forgot what that unit is. It's deleted. But if you look at it 1 there, and you read this number as a height, right? So that was negative 0.47. Remember that? So it tells you the position was up there. It's just roughly like 3 units up, right? But the velocity, average velocity over 100 seconds was negative 0.47. Let's go to the 3 seconds. 3 seconds, what this graph is telling us is it's roughly, what was that number? 3.1. This is 3.1 roughly there. That's the average velocity if you go back there. And this is a position, just roughly 0.7 units up from the center position. And the next 100 seconds is a slightly upward, and that velocity, how fast it was moving over the 100 seconds, it was a 3 unit per second. That's what it's moving, right? Okay. How about this one? Does it look like 3.25? Is that rough estimate, all right? 3.2, 3.5 in here. Let's say it's 3.3. It's better. So what's happening after 3.3 seconds later to this particle? Right, this value, y value here is a 0, right? All the y value here is the velocity. It's VA. Velocity is 0. At that point, like 3.3 seconds, this particle stopped. Whether it continued going after stop or coming backward, it stopped at that instance, right? Let's go back to 3.3 here. It's roughly up there. You see that position? What is happening at that position? Is that just like at the stop sign, you drive a car, you make a complete stop as the law requires, and then move on. That's a speed 0 and move on, right? Is that the case? Or stop and you forgot something and return and going back? Which case is that if you're looking at this position in here? If it is keep going upward, you have to go up, right? But the position is repeat going back down. So is it turning the direction? That's why it stopped in there. So these are the two things. Velocity function, average velocity function, that's what I call. Average velocity function with interval h, and this is a position function, right? This is good information. 100 seconds is, according to the motion in here, pretty good information on how fast it was actually moving at instantaneous velocity. Gives you a good idea. All right, so I think I explained that. All right, so those are V bar, but for free we have also M bar. I don't think I introduced M bar in here, but you know the meaning of M bar? That's the slope, that's the, this MA, I'm going to call that was secant slope function. This is also non-standard term, secant slope function. Is that all right? Term make sense? Secant slope function. So if it is not motion, if it is just purely just function y equals s of x, and what this red curve represents at each stage is the secant slope of a secant line. All right, let's try that. For example, I'm going to go and estimate by looking at this graph. This is in the correct scale, all right? So I'm going to go, for example, what is m bar of 2? The meaning of m bar of 2, can you somebody describe the meaning of m bar of 2? Clear in English phrase? Is the slope of what kind of line? Secant line at 2. Thank you. At 2 with interval h, which is here set to 0.100th, right? 0.01. So you go to 2 here. This is where the original graph is, right? So go to 2, back down. Does it look like a position? And after 100 units later or seconds later, where is that position there? So right next to it. Would that be fair enough? So almost you look at that segment. If you look at this segment, for example, here, you know it's a slightly curved, right? But isn't that easy to go and just straighten up? And this is it. This almost look like that little line segment, right? If you go down to the 100th level and 1000th level, that's small, you know, a curve doesn't look like a curve, it's just line segment. You take that just line segment in here, that looks like just line segment. Just continue it like that. Forget about that, you know, the tiny thing there. So maybe look like this. Does it fair enough? That's the line that connects that two position. They're like 100th units apart from each other. So if it is in the correct scale, what would you your estimate of here is ms. That's a number, right? M bar is the name of the function. What was your estimate roughly there? Negative 1.5? I think that's what it looks like. Slide it towards the vertical more side. So that's my estimate, negative 1.5. What's the truth here? You go here, 2 there, right? And it tells you what the average velocity is. It tells you what the slope of the secant line is. So you go down vertically. Is that correct? I was way wrong. It was more than negative 2. It says it's almost negative 2.2 or something like that, right? So that was actually way off, and the correct answer was negative 2.2 was the slope of that secant line. So interpretation of these two things makes sense, right? Often we actually put this one together in one coordinate system, all right? But it's better to separate and interpret it first. So let's go back to Sage and plot these two things together. Okay? Does anybody know how to do that? Right, we show what was the first thing? It was that position, right? And plus, what was the second thing called? The velocity picture. So if you do that with correct aspect ratio, because we're comparing the slope there, so better be in the correct aspect ratio. If you do that, it shows you the graph there. The blue is actually the graph, and red is telling you what the slope of a secant line is and what the average velocity at that point is with a time interval 0.01 second, right? Okay, so I'm going to copy that one and particularly pay attention to interesting point, extreme points we say. Let's hope I can fit this one in. There. Okay, so let me go ahead and position that point right there. If I pick that top points there, what is happening? What is interesting things happening at that top position at that instance? That's almost like 1 second, right? What is happening at 1 second in terms of the descript motion? Kind of going up and changing direction is coming down, right? At that instance, you can intuitively argue that it must have stopped before you change the direction. You can't just abruptly change the directions, right? So let's think about average speed. At that point, at 1 second, you look at this red curve. What is happening to the value of the red curve around that 1 second there? So almost 0 is hitting the x-axis, right? The horizontal axis, right? What does that mean? Velocity is denoted by VA is there roughly 0. So this velocity graph is telling you when the velocity is 0. So see if same thing is happening down here, almost like 2.2 seconds, right? What's happening? It was going down in terms of motion and changing it going up. If you look at that time position, you can see the velocity is hitting 0, right? How about around this position? Over a certain period of time is rapidly going up. Would that be the fair estimate of the description of this instance? That instance is moving up, but actual motion is going up that way. If you look at the speed is up there. The magnitude is like 4, and relative to other position, it was rapidly moving. It's moving fastly upward at that position. This one telling you the speed is negative magnitude. It's going down fairly quickly, but not as fast as going up in one period before. So if you juxtapose these two graphs on top of each other, you can make sense out of a lot of things, right? So these are the position and average velocity put together, right? And we can make sense out of it. All right. I just heard that test is coming up, so we gotta buckle down and work really hard toward it. So here's an example. S of t What is S of t standing for usually here? Position, right? So I give you a simple formula, like complicated transcendental functions. It's a simple thing that we can handle. Don't forget about the graph or anything. Just think about the concept. S of t is a t minus t cubed. Is a position, right? The position. So where is this thing at 0 second? 0. What is this after 1 second? 0 again. So what is the average velocity of this thing over 1 second period from 0 to 1? 0, right? So, but that's not really what happened. It's not a good information. But if you narrow down, it's going to give you good information. So what is h is going to be? Maybe 0.01 again, right? 100 second. All right. So that setting is given. And what was that newly derived function? Remember that? What was that called? V bar. What was that? V bar of t. Is that right? Or V bar of a. Let's write down the formula. V bar of a. Average velocity function with the interval h. That's what I called. Nobody calls like that. It's just for this class purpose. A. What was the formula? S of a plus h. H is that number minus S of a divided by h. That's the formula. We use Sage to compute the values of this one because sine and cosine is scary, so we didn't even do anything. But here, t minus t cubed, right? You learned that in like 10 years ago, something like that, or probably more than that. So let's actually go ahead and calculate this one, right? All right, let's compute it. Everybody's up for the tired of Sage. We actually calculate this. Let's compute v bar of a. Don't leave it like that. Just actually plug it in there and calculate it, all right? All right, let's do it. So v bar of a is, putting this 1 over h to the side like that. Does that make sense? H is down there. It's a long horizontal line. I don't want to do that. 1 over h. Set aside. Good? Let's do that. This is going to be S of a plus h. This is going to be S of a. Make sense? That's going to be a placeholder. You see that? 1 h in the denominator set aside, numerator 2 terms, S of a plus h and S of a. So you plug in S, let's do this S of a first. What would be the second slot in here? It's really simple, right? A minus a cubed. Fair enough? You plug in a in there, so it's going to be a minus a cubed. Correct? Let's do this carefully in the first one. Input here is a plus h, right? Every place where t is, a plus h will occupy that place with parentheses, right? With parentheses. So you see the t there. T is replaced by a plus h. That's what the input here is, right? With parentheses. So put parentheses and rewrite that a t part with parentheses a plus h. Minus, there's a t again. That t is replaced by a plus h with parentheses, right? This is a plus h. Parentheses. Excited, right? Wow, I'm so excited. I'm going to go and expand all that and have fun. And all that, right? So let's do that. All right. Here in this, when I do this lecture, I use this bracket parentheses so that it's distinguished from the confusing parenthesis, but you should never use this one in Sage. You always have to use this round parenthesis, all right? So the big parenthesis there, well, a plus h there. And you expect that after you expand this a plus h, it's going to be long, right? It's not going to be a cubed plus h cubed, right? And let's just expand that out as negative a plus a cubed. Is that all right? Close the parenthesis. Let me actually delete that additional parenthesis. Would that be fair enough? Okay. All right. So if I can write down a plus h cubed, and that's going to be the answer, right? You fill in there and then simplify. Make sense? All right. Let's do that. All right. This is a binomial expansion. The binomial expansion is 2 times raised to a power. So here's how you do it. 1 and 1. this is a plus h. These are the coefficient of a and h. In front of a, there's 1. In front of h, there's 1, right? So you write it like this. If it's a minus h, you still use this 1, 1, all right? It's just like a placeholder. There are two terms represented by 1 and 1, really representing the coefficient, right? You square it. What you do is that you write down always at the beginning and at the end 1, and you add this to number. That's 1, 2, 1. Make sense? This is called the Pascal's triangle. This is a coefficient of a squared term and ah term and ah squared term, right? If you raise the third power, you always write down 1 and 1 there. And you add this two number, write down in between 3, and add that two number, write down in between 3. If you think about this principle, if you actually expand it, write down a plus h, a plus h plus h, multiply it out, you can explain why it works like this. It's really fun to play with that. So what that does is that you start with the first term raised to the third power. Next one, you reduce the power, but h kicks in. And next one, power of h goes down, and power of h, a goes down, and power of h raises like that. And a disappears, and it becomes h to the third. That's what happened with a and h. What you do with this number, and you put those numbers in front of it. 1 and 3 and 3 and 1. That's the result of a plus h cubed. Okay? So that's all we need. But just for fun, let's go and write down a plus h to the fourth power. All right, let me go ahead and circle that. 1, 3, 3, 1. Yeah, what is it? So let's go and apply, yes. So if I have focusing, although there's actual math formula, let's focus on, 1, 3, 3, 1. Does it look like the number in that Pascal triangle tree? Right? So by just focusing on that number, let's move on to the next level. You see that the first number is 1. Next number is sum of these two, right? 4. Next number, 6. The next number, 4. And 1, right? That's how it's going to happen. But you start with what power? The highest power, a to the fourth. Okay? What is the next one? You go down by 1 power and h kicks in. But what was the coefficient? The very first one is always 1. But next one is the sum of these two, right? Therefore, it's a 4. Make sense? What's the next one? 6. But what about the power of a? It goes down. H is raised again. And what was the next coefficient? 4 again. What about power of h? Go down. And power of a go down. And power of h goes up to 3. What is the last coefficient? Always 1. And that kicks up h to the fourth. That is actually the result of a plus h raised to the fourth. This tree is called Pascal's triangle, and it is a fundamental subject of lots of counting and combinatorial objects. It's a really fun thing to, group that part and think about the sum of all that thing. And there's just a book about this coming out of this, calculating things about the triangle. But it's a fundamental part of algebra, right? It's a fundamental part of mechanics, the fundamental part of the way the quantities interact mathematically in the nature, right? So it's not like some fun puzzle. This is the way the world operates, with a bit of exaggeration. Why did we do all that? Go ahead and replace that a plus h with a, expanded term, right? And what was that? It's a cubed, 3a squared h, 3ah squared plus h cubed, right? Make sense? All right. Now, 1 over h is still there. And see if you can cancel out some of the terms, right? Cancel out some of the terms. So go ahead and find out the terms that's repeating. Do you see that? Some cancellations. First term is a. You see same a appearing with opposite sign? It's right there, right? Double line. Make sense? So they cancel. I don't see h in any cancel, but negative a cubed there is, right? Negative a cubed. But you see positive a cubed? Positive a cubed. They cancel. Usually, when you calculate average velocity function or whatever the velocity function you do in that course, that thing that in the second slot of the original formulation, they always disappear. Don't think about trying to cancel anything else. Just that the second term here, they all disappear from that calculation, right? If it is a polynomial. Make sense? So we focus on, all right, let's do next part. So h stays there, and negative a cubed is gone, right? But negative 3a squared h stays, correct? And negative 3ah squared stays, and negative h cubed stays. Is that correct? So these are the four terms that stays. All right. Everything has h in there, right? It usually appears like that. Time interval is short. The actual displacement over time interval you expect is very short, right? So does that look like approaching 0 divided by approaching 0? Does that make sense? Our definition is a quotient of two things, right? This is average velocity function, correct? If the time interval is very short, do you expect the displacement of the particle is also very small? Right? So is that like approaching 0 divided by approaching 0 if our time interval is very small? Because of that, we expect this cancellation. H always disappear. All right? So that's why we have h there and h there and h there and h there. And down there, we have h there. Don't leave it like that. What do? You factor out and cancel. So 1 over h, you factor out. Now change the usual parentheses. What happened to h? Invisible 1 shows up, and h is factored out. But there is still h sitting in there, right? Like that. What could happen is that there's a denominator before, and there's no more denominator. This is exact formula. 1 minus 3h squared minus 3ah minus h squared. There's clearly the terms that are separated where h is involved and h is not involved, right? So I'm going to put that mark in there. But that's our answer. That's our better formulation than this bulky one, so that when you have to say something about the behavior of this function, you have a better things to say. It's easier to analyze. You're looking at this polynomial easy expression, right? And what was the h value? We set to 100th second, right? So, if you multiply 100th to 3a and that, it's this insignificant term. Would you say that? Insignificant term in terms of its magnitude. It's very small. If you multiply 0.01 to these quantities, it's very, very small, right? And this is a main term. So when you calculate average velocity, it can be often separated by the main term and insignificant term, which involves h in there. Make sense? All right. So that's that, and we're going to go in and put. So now from that conclusion, we have v bar of a now have this formula: 1 minus 3a squared minus 3a h minus h squared. This is something we deduce. So let me write it like this, right? Hence, we calculate it like this. Make sense? We can sketch it and all that. So let me introduce at this stage. That's that. So I think I'm not gonna use Sage. I'm just gonna use my knowledge of how these two things will look like. All right. So I'm gonna sketch y equals st. What does st represent? Position, right? If you sketch the position, it looks something like this. Here's a 0 second. It goes upward and coming back down a little bit faster than while it was going up, between 0 and 1 second. Remember the average velocity between 0 and 1 second was 0? Because we checked that at the 0 position, after 1 second it was on 1 second position. That was t minus t cubed. That was the formula. Make sense? All right. If you sketch that, what is it? Average velocity function, it's going to look something like this. Roughly, there's a velocity 0, and I think it's a positive, it's supposed to be square, so it's something like that. So I skipped the Sage part. I sketched this function where h is 0.001 and h is 0.01, and if you sketch that y equals v bar t average velocity function, it looks like that, right? And I put this marker in there. That's where the velocity VA, right? I'm using this VA notation. What is that? 0 at that instance, right? Is that kind of consistent with the observation of behavior from the black part? Does that make sense? You're going up and coming back down. It stops. Velocity at that instance 0. So it looks roughly like that. All right? So that's the end of discussion about what? Average velocity function, right? Average velocity function. So instead of just calculating average velocity here and there, I try to introduce this as a newly derived function. And that's the key part, right? Okay? So if it is insignificant part like that, why do we bothered with like this? What if we take that h to be, 0.000000 whatever the limit of our measurement capability, go down that level, and then you can see while h is almost 0, whatever you have it here is going to be almost 0, right? Immeasurable quantity is 0. So why don't we just drop that, right? And take that main part as that's the idea of instantaneous velocity. If h is approaching 0, what could happen to the VA? That's the instantaneous velocity. All right? So let me write down that notion and calculate the instantaneous velocity function quickly from that notion. So here's a notion. What's VA? Average velocity with interval h, right? Usually h is small, but it doesn't have to be. That's a notion. So it looks like that, for example, in that example which is calculated. At various different time slot, it looks like that, right? So as h approaches 0, if you look at this example, this is the average velocity at various different time position A, right? Time slot A. And this is going to be approaching, in that case, nothing, there's no h in there, and obviously by limit laws, this guy approaches 0, correct? This guy approaches 0. So it's like have a nice behavior. If I set the h approaches 0, this becomes something. The limit exists. Does that make sense? This VA involves this time interval in there. If I take the time interval shorter and shorter and shorter, then the behavior of the average velocity, in this case, if you look at here, very nice. There's 1 minus 3a squared, and this guy disappears according to the limit laws. Correct? So it exists. V. It's just V. All right? With no subscript is the V. It exists, right? What is this idea called? Not average velocity? The instantaneous velocity. Is not h equals 0, is the behavior is defined. That behavior is the idea of instantaneous velocity. When you start a car, the speedometer of your vehicle is not telling you the average velocity, right? It is actually constantly changing and telling you what the instantaneous velocity of the vehicle is, right? Your speedometer is telling you that at that moment what the velocity is, right? I don't know exactly how it does it, but I'm sure it's actually doing that using a very short time period, like 1,000th second. So it is actually average velocity with 1,000 second. But mathematicians can kind of imagine actually the behavior limit is really this instantaneous velocity with this insignificant part disappeared, right? Make sense? That's the notion of a instantaneous velocity coming from average velocity. But here is the more difficult part, is that we have not only the average velocity, we have the function v bar t. We have the function v bar t, right? Okay, what was v bar t? Average velocity function with h involved in there, right? So as h approaches 0, each of this v bar a, for example, if you're looking at a certain time slot, that is actually the v subscript a, just a number. And what happens to that? It approaches some number, the v, right? Instantaneous velocity. And then at each point at a, we get this new value. So does it look like an algorithm? I give you an a, compute the average velocity by changing the time interval shorter and shorter. So that's a new algorithm, right? So that gives you another newly derived function. Function from what function? Originally from st and via this average velocity function v bar t, right? Using these two idea, sending h approaches 0, we have a new behavior that that is called. So this is idea, this algorithm. Given a, we got instantaneous velocity. That is the output value, called just v. All right. The arrow is the description of all procedure that I describe as algorithm. So I give you an a, you calculate instantaneous velocity. I give you a different a, you calculate different instantaneous velocity. Does it look like a function? Right? That's a function. Right? So that is the main subject of this entire course. This function I just described. All right. I'll continue with this thing tomorrow.